doing okay this day? Yeah? Look, I have your exams. I did well in the exam. The exam was pretty good, so I'll return it at the end of class. And I've already posted the GPM online, so I'll return that in just a bit. Let's do a few questions to sort of recap what we've been doing so far. Sort of big picture kind of stuff. Alright, so I'm going to ask you a series of questions about electric forces. B, electric fields. C, electric potential. D, potential difference. And E, potential energy. These are all topics that we've talked about in the past few class periods, couple of class periods, I guess. Potential energy. All right. So first of all, which of these must have two or more charges to be in effect? Which of these must have two or more charges? Forces, fields, potential difference, or potential energy? Which of those are required to have two or more charges to occur? Only one of them requires two charges. All the others can occur with just one charge. All right. Just a few more seconds. I'll stop at 55. All right, A is right. You have to have two charges for forces. I remember we saw the expression for that force gives by Coulomb's law, F equals K Q over distance squared. Let's say that I have two charges. Say I have two charges here. They're separated by 2 meters, and they experience a force equal to 10 newtons. All right. If I double that, like let's say that I let D equal 4 meters, what is my new force? Is it A, my 2.5 newtons, B, 5 newtons, C, 10 newtons? I mean, it's the same. Or is it D, or D, 20 newtons, or E, 40 newtons? If I double that distance between these two charges, I have two charges here. They're separated by 2 meters, and the force between them is 10 newtons. If I pull them apart, the 4 meters apart, now what is the new force on these two charges? 2.5 newtons, 5 newtons, 10, 20, or 40 newtons? That is the force quartered, half, the same, double, or times a factor of 4. 1. Has somebody left their book in class last time? Is that any of y'all? What kind of book was it, Ellis? Did it have anything on it, marked in it? Okay. All right, I'm going to stop at 125. 125. Oh yeah, we're all over the place here. So A is the right answer. If I increase D, what I'm doing here is I'm doubling this. I'm doubling this number. But because it's squared, that 2 that I'm doubling it with, I'm going from 2 meters to 4 meters. Because D is squared, that really means that I'm having a 4 in the denominator. Right? So that means that I'm going to take a quarter of the original force. So where it was 10 newtons, now it's going to be 2.5 newtons. What if I kept this the same, I kept the distance the same, so that goes away. I keep them at 2 meters, but I double one of the charges. So before, I had Q, I had Q, Q. What happens if I make one of these charges 2Q? So I just make them bigger. What happens then to the force? So the distance stays the same, but I'm just doubling one of the charges. What happens to the force that acts on those two charges if I double just one of the charges? Is it going to be 2.5, 5, 10, 20, or 40 newtons? Okay, we want to look at this expression that we have here. This F equals K QQ over D squared. What I'm saying is I'm taking one of these charges Q and I'm doubling it. I'm making it twice what it originally was. So now I want to know what happens to my force F. All right, take just a second to ask your neighbor what they put, okay? Only about 6 of you have the right answer, and about an equal number don't have the right answer. So ask your neighbor, if you double that charge Q, just one of the charges, what happens to the new force? That's a little better. I'm going to stop at 125. 125. Good. D is the right answer. If I double that force, if I double one of the charges, it makes for a bigger force between those two charges. All right, let's, one more question. This is a little trickier. Let's say I'm keeping the same charges, so this 2 goes away. I have 2 charges of charge Q. And then I make the distance between them not 2 meters, but 1 meter. So what I'm doing here is I'm taking half of that distance D. So where I have D here, I'm now going to have 1/2 D. So I'm going to imagine that I put in a factor of 1/2 here, and I want to know how is the force affected. Is the force going to be 2.5 newtons, 5 newtons, 10 newtons, 20, or 40 newtons? Let's write this back. You'll see a couple of different questions like this regarding forces, fields, and potential. Sort of as you change things, how does it affect the force, field, or potential? These are good questions for like standardized tests too, like if you're doing any of the various admission tests. I like to ask these kind of questions. As on these questions, you want to ask yourself first, is the force going to increase or decrease? So I have these 2 charges right here, and they experience a certain force. What happens to the force if I bring them closer? Don't worry about the equation, just ask yourself, what happens to the force if I bring them closer together? Does it increase or decrease? It increases, right? So the force is going to get bigger. So that means I can get rid of A and B, and I can get rid of C as well. So I'm just left with D and E. That's a good practice for example in general, is that you eliminate a lot of the answers. And you can just do that just by saying, well, I know if I bring these charges closer together, that the force is going to increase. And then you can ask yourself, well, by what amount? Is it by a factor of 2, or is it by a factor of 4? All right. Let's see. I'm going to stop at 135. E is the right answer. If I have this expression and I have a 1/2 here, it's going to be squared. That means that I'm going to get a factor of 1/4 in the denominator, but 1/4 is going to equal to 4. Right? So if I have a 1/4 in the denominator, that comes up on the other side, and I'm going to get a factor of 4 here in front of my force. So I'm going to, where I had 10 newtons, I'm now going to have 40 newtons by bringing them twice as close together. or by halving the distance. All right, of these 5 over here, which of these is a measure of energy per charge? Which of these is a measure of energy per charge? Is it the forces, the fields, the potential difference, or the potential energy? Which of those is a measure of energy per unit charge? Many of you have the right answer, so we're about evenly split. I'm going to stop at 42. All right, C is the right answer. Very good. Energy per unit charge, that's a measure of potential. What's the units for potential? When we talk about potential, what are our units? Voltage, right? It's volts, right? It's the potential is what we get out of our electrical outlet. So that's when you talk about the potential of electricity or the potential of an electrical charge, then that's a measure of energy per charge. Which of these, A through E, is measured in units of newtons per coulomb? Don't think about the units, right? Think about what these units are measuring. A newton is a unit of what? Force, right? And a coulomb is a unit of what? So I'm asking you now, which of these is measuring force per unit charge? Which is measuring a newton, which is a force, coulomb, which is a charge, which is a force per unit charge? I'm going to stop at 48. All right, good. B is the right answer. I thought you were going to get them all right there for a second, but then I had a couple people come in. Thank you. I don't really feel like telling jokes today. Is that okay? Oh, wow. Yeah, I don't feel very good. All right. I'm not sick. I just don't feel well. All right. Let's see. Let's go to the next slide. Oh, so fields is force per unit charge. So in the big scheme of things, forces is just the force between charges. And then related to that, I get from forces, I get a force per unit charge. Fields can exist with only one particle. So forces have to have 2 particles. So fields can exist with only 1 particle. I have this particle, and the field around it describes the force that a particle would feel if it were to come close to it. So fields only exist with 1 particle. You can have more than 1 particle and have a more complicated field, but you can just have it with 1 particle. Potential is a measure of energy per charge. Potential difference is the difference in potential between 2 different points. Just a second, we'll talk about this more. And then potential energy is just like our potential energy that we talked about before. Gravitational potential energy is just as it relates to electrical charges. All right. Oh, and actually, I guess potential energy, you have to have 2 charges for that as well. In order to have potential energy, you have to have 2 charges. Because you think about these charges that come together, if I have 2 positive charges and I hold them right here, they have potential energy. Because what's going to happen if I let them go? Well, if they're positive and negative, yeah, they'll stick together. But if they're 2 positive charges, they'll fly apart. And that's what potential energy is. It's the potential for motion. All right. Between 2 points in space. So if I imagine, well, let's just think about a wire. Say I have a wire here. I would find the potential here, VA, and the potential VB here. The potential at those 2 different points, and the potential difference, which people often call delta V, would just be VB minus VA. It'll be important when we talk about cell potential. There's a potential difference, a difference between the potential inside the cell and outside the cell. So we talk about that in terms of potential difference. It's very similar to potential though. Same unit, same idea, energy per charge, except just the difference between 2 points in space. Let's see, what else? Going back to my notes. We don't have much longer left. We just have Tuesday and Thursday. And I guess that's it, right? Because the next Tuesday is our last class day. And we'll be meeting over in the rec center. Is that right? That's right. Yeah. All right. They're on the last class day. We'll do them over in the rec center. All right, there's a projector and all that. We're gonna meet in the classroom upstairs. I'll send y'all an email about this later. All right. Still don't know what we're gonna do over there. I'll figure it out. We'll do something fun and exciting. Right? Yeah, we do have a quiz on Tuesday. That's on the 28th. Right. So there'll be a quiz on this chapter. Okay. I'll send y'all a reminder. Thanks, Carly. All right. Pages here. Okay, let's look. Oh no, I want to ask you one more question. Let's say that I have 2 points in space. And I have this point over here. It has a potential equal to 20 volts. And then I have another point over here. It has a potential equal to 10 volts. Right? This is a measure of energy per charge, right? A charge at this point would have 20 volts or 20 joules per coulomb. It's an energy per charge. Over here, it would have less energy per charge. So I want to ask a question now. Somewhere between this first point and the second point, the energy per charge decreases. What happens if I put a positive charge here? Which direction will it go? Will this charge move to the right? Will it move to the left? Or will it remain stationary? I have a potential at one point. On the left, it's 20 volts. On the right, it's 10 volts. So somewhere in between, I have this gradient of voltage. So as I move from this point to this point, the voltage decreases, or the potential decreases. So I wanted to ask the question is, if I have this charge here, which direction will it move? Will it move to the right, to the left, or will that charge remain stationary? Just stay where it is, it won't move at all. All right, so a few more seconds, I'll stop at 50. 50. Very good. A is the right answer. Because objects in general move in the direction of increasing or decreasing potential energy. Like if I have a stone on a hill and it rolls down the hill, what's happening to its potential energy? Increasing or decreasing? It's decreasing, right? Because it's dropping its height. And a similar thing for charges. Objects in general move from from high to low potential energy. And that's what this charge is doing. It's moving from a point of high potential energy to a point of lower potential energy. Remember, voltage is just potential energy or energy per charge. So this guy is moving from a point of high to low potential energy. I can think about this in terms of, we sort of talked about this, but I can think about this in terms of I have two metal plates where one is positively charged and one is negatively charged. I could have this plate be V equal positive 20 volts, and over here, instead of having 10 volts, I could have negative 20 volts. And so a positive charge would move from the big side on the left over to the right side. I can also draw my field lines, describe the field. If I draw field lines, they look like this. That charge will follow the field lines, Or I can also think about the forces at work. All this is sort of wrapped up together. If I have positive charges over here, it's going to be repelled from those positive charges. If I have negative charges over here, it's going to be attracted to those negative charges. All of those are going to make it move to the right. Those are all ways of saying the same thing, right? Because they're all related. The fields, forces, and potential are all related to one another. Okay? Okie dokie? All right. Let's look now at capacitors. I think that was the next topic. Let's see, we did potential difference before. Oh no, so yeah, we talked about how objects move to lower potential energy. Is that right? Like the hill on the stone on the hill? I don't remember. Okay, maybe y'all just knew that. Did y'all just know that? You guessed? Okay. No, the thing is with negative charges, we'll see it's a little bit just different because if I put a negative charge here, it's going to move to the left. All right. Yeah. Okay. All right. So that sort of ties in with this topic: electric potential difference and potential energy. Electric potential difference and potential energy. So if I have this charge that moves between two different points, for example, if a charge were to move across a cell membrane, which we'll talk about next time, it experiences a potential difference in the energy of that charge changes. So let's say that we'll say I have this cell membrane, and I have a positive charge over here, and it moves from this point over to this point. And then there's some potential here, I'll call it V1, and then there's some potential over here, I'll call it V2. Now the potential difference between those 2 points, as he goes from this point to this point, the potential difference, which we call delta V, is equal to V2 minus V1. All right, I just take the potential at its final location, subtract it from the potential at its initial location, and then my potential difference is just a difference in those two numbers. All right, so this charge is going to experience a change in energy. And it's given by this. U is our change in energy, or is the energy of this charge, actually delta U, because it's changing, is equal to Q times delta V. This comes back from our definition for V. So let me write this up here in like a little thought bubble. V, remember, is U divided by Q. That's sort of our basic definition of our voltage, our potential energy. U is just energy divided by Q. So that's just sort of reorganizing this and saying, now my change in energy for this charge is equal to Q times delta V. So if I have a positive change in potential, if delta V is positive, I'm going to have a positive change in my energy. That also comes about here that, Caitlin, what you were saying, if Q is negative, then it switches how we were talking before. That if Q is negative, that means it's going to move from a lower potential to a higher potential, whereas positive charges will move the opposite direction. Don't sweat that too much, but this delta U is equal to Q times delta V. Charges tend to move to lower potential energy. just like all objects, like a ball rolling down a hill. Have we done this? We have not done this. Is that right? Give me just a second. Let me look. I thought we had covered this topic. Right here. This is something different there. So this is related but different. Sorry, I'm not quite all here today. So charges tend to move to lower potential energy, just like that stone rolling down a mountain. So positive charges will have a negative delta V, and negative charges will have a positive delta V. Let me show you. So we have this equation, delta U equals Q delta V. All right, delta U is negative. That's just sort of in general for all objects. They're going to move so that their change in potential energy is negative. That's like your ball dropping in the Earth's gravitational field. So if Q is positive, that means delta V has to be negative. All right. If Q, on the other hand, is negative, that means delta V has to be positive. So if we go back to our metal plates, I have these metal plates. This one's positively charged. This one's negatively charged. I'll call this one plus 20 volts, minus 20 volts. If I have a positive charge here, it's going to move in the direction of decreasing potential. All right, so for it, delta V is negative. So for example, my delta V for this charge will be negative 20, that's this voltage, minus 20, which is negative 40 volts. On the other hand, if I have a negative charge, it's going to move in this direction, right? So that its change in potential is positive. And so I can think about this, 20, which is my final voltage here, minus a negative 20. So it experiences a delta V of 40 volts, whereas the other one experiences a delta V of negative 40 volts. Does that make a lick of sense to you? Sort of, kind of. It's important because later, like I said, when we talk about cells and how the neuron works, it works by this idea that I have these charges that are moving in and out of these different potentials. All right. So if y'all have had, I think you've had anatomy. Yeah. Do you do neurons in anatomy? Do you talk about the charges at work? Well, inside the neuron, inside the axon, I think that long thing, is it called the axon? Yeah, it has a negative potential, and then outside you have a more positive potential. And so charges will tend to move back and forth because of this idea that when I have a positive charge, it'll move in one direction or the other, and negative charges will move that opposite direction. So we'll come back to this idea. All right. Okay, it is possible, and your book talks about this, though not very much, because I think that the biology of it is fairly complicated, but it is possible to move charges so delta U is positive. Right? But this requires some amount of work. So like if I have this desk, I lift it up here, if I let it go, it's going to go down. That would mean that its delta U is decreasing, its delta U is negative. All right? But if I have it here, like normally it's not going to go up. What do I have to do to make it go up? To make delta U be positive? I have to do work on it. I have to lift it. So I have to do work in order to make delta U positive. And your body does this, what's it called? So your body can do this, move charges so that delta U is positive, but it requires some outside energy source. your neuron, that's called the sodium-potassium pump, I think, which uses ATP, if I'm not mistaken. I don't fully understand the chemistry of that, but we'll get into it a little bit. And I'll probably know more about it than I do. Right? It's very confusing. I've been trying to. I read the chapter about 15 times last week and read some other materials, but it doesn't help very much. The 2-minute neuroscience videos? Okay. Well, I found some as well online, so. But we're not terribly concerned with the chemistry of it. Alright, let's look at capacitance. We're not going to talk much about capacitance later, but in the neuron, it does act as a capacitor at certain times. So we're just going to sort of brush up on capacitance. A capacitor is a device that separates negative and positive charges. I've been drawing capacitors all along. Usually a capacitor is just 2 metal plates in a circuit. If I have a capacitor in a circuit, it's just 2 metal plates. When that capacitor is charged, it has positive charges on one side, and then it has an equal number of negative charges on the other side. These plates never touch, but they just hold these 2 charges separate from one another. In doing this, it's able to store energy. So one of the primary purposes of a capacitor is to store energy. Usually these things, I'll show you a video in just a few minutes, but usually these things are separated by an insulator. And that prevents the charges from traveling from one side to the other. So if you have these 2 metal plates, the tendency would be for these charges to jump across if they could, but if they're separated by an insulator, those charges can't jump across that space. I'll show you how they look in a circuit. You've probably seen capacitors. You ever seen a capacitor on a circuit or whatever? You probably have. They're sometimes like really small and sort of cylindrical. If you've ever opened up your computer or seen any sort of circuit board, you've probably seen a capacitor. They're fairly common. If I have a circuit, it looks like this. This is a battery. This is the symbol we use for a battery. This is the positive side. This is the negative side. What happens, or what we think of as happening, this isn't physically what happens, but I will get positive charges that will move over here so that they rest on that plate. And then negative charges will move from this side over to this plate. That's how we think of it as happening. Actually what happens is I just get negative charges that come across here, and then they induce a charge on the opposite plate. So they basically force away the electrons that were over here, and they come over to this side. But the end result is that I get positive charges on one plate and negative charges on the other plate. So if I hook up a capacitor to a battery, it puts charges on that capacitor, and then I can take the capacitor out of the circuit, and I can use it for whatever I want. So now I have this energy. I have this energy stored up in this capacitor, potential energy, and I can use it for a number of different things. All right, so I have energy stored now in the capacitor. Capacitor. I'll go down just a second. Can I go down now? Say my little girl's turning 7 tomorrow. My little girl's turning 7 tomorrow. Did I tell you that? No, it's true. She's turning 7. Do you know what we're getting her for her birthday? What do you think we're getting her? A what? No, she has a bike. What would be like the best thing you could get for a 7-year-old girl? A what? A close, but fit too big to have a little bitty house, huh? Not a pony, no. Not a dog, we have a dog, but a cat. Yes, we're getting her a cat.
Close to a horse.
Huh? Close to a horse, but not really a horse, yes. A mammal with 4 legs. Alright, don't tell her. Okay. What was I doing? Oh, so a capacitor looks like this. It's one metal plate and another metal plate. So each of these metal plates, let's see if I can draw it in 3D. I have one metal plate there, right? It has a certain area, and I have another metal plate here. They're like this, right? They have a certain area, and they also have a certain distance by which they're separated. So I have an area of the plates here, and then I also have the distance by which they're separated. The capacitance measures the device's capacity to store charge. Alright, I want to ask you some questions. If A is bigger, so if A goes up, what happens to the capacitance? Does the capacitance A go up, B go down, or C, does it stay the same? If I make the area of these plates bigger, will it be able to store more charge? That means it has a greater capacity to store charge. Will it be able to store less charge, so the capacitance goes down? Or will its capacitance remain the same? If I make the area of those plates bigger, what happens to its capacity to store charge? No reason you should know this right off, but I think that you probably do know it. If I make those plates bigger, what happens to the capacity of them to store charge? Does it increase, decrease, or stay the same? Alright, I'll stop at 55, 55. Alright, good. A is the right answer. Thank you. Never put B. Thank you. If I make them bigger, just think of them as like a big pot, right? You can put more water into a bigger pot because it's bigger, right? So if I make these plates bigger, I can just store more charges on them. What happens, on the other hand, if D increases? So if instead, that is, I separate the plates, I pull them apart, what happens to their capacity to store charge? I might not know this right off, but I want to see what you think. If I pull these plates apart, will they be able to store more charge? That would be A. Store less charge? That would be B. Or will they store the same amount of charge? That would be C. Alright, I'm going to stop at 55, 55. Y'all showed all over the board on this one. So no reason necessarily that you'd know the answer. Alright, B is the right answer. If I pull these plates further apart, that capacitance is going to decrease. This is all wrapped up in the equation for capacitance. You'll have it on your equation sheet, of course, but it looks like this. That C is equal to area divided by distance. So think about this. If area goes up, C goes up. If D goes up, C goes down. There's also some constants here. Don't worry too much about these constants. This is called the permeativity of free space. And then this is the, gosh, what's that called? The dielectric constant. So this insulator that you have in between the two plates, that's called a dielectric, and this is just a dielectric constant. It's just a number. All right, but the important things are this area and the distance between them. Hey, I have a little clip I want to show you. This is from Make Zine. Let's see.